you very much for inviting me to give this seminar to this very broad and wonderful audience here. So I will tell you something about the out of equilibrium quantum dynamics of nuclei stimulated by a laser pulse and how we can actually simulate it with first principle calculations. And I'm going to dive into a very peculiar system, which is strontium titanate, and we will see a few slides why. And in particular, we will shine this material with the terahertz laser, which is infrared light. And this is an example of pump probe spectroscopy, which is very useful to probe out of equilibrium properties of materials. So how does it work? We send a pump, usually a laser pulse, in this case will be a terahertz laser pulse into the sample, which must be very short in time so that we can this pump probe pulse drive the system out of equilibrium, and then we probe properties of the system after a certain amount of time, which can vary. And in this way, we can probe properties of the system as it is evolving and as it is propagating in its out of equilibrium nuclear dynamics. In particular, we will use terahertz light, which is in resonance with phonon excitation. So we will excite a phonon of this material out of equilibrium, and we will see the dynamics of atoms, how it evolves with time. And there have been used many different probes. We will see some of them. They can be X-ray to have actual much nicer information about the actual position of atoms, or they could be something else that I will show you. So why do we want to study strontium titanate? And the reason is that strontium titanate is a very interesting material at very low temperature because it's a quantum paraelectric material. So it means that if we follow a soft phonon modes whose phonon displacement breaks inversion symmetry and generates a polarization inside the cell, this energy of these phonon modes decrease with temperature. And if we do a fit, a classical fit following the Curie-Weiss law, this should become imaginary at a certain finite temperature, which is around 37 Kelvin, and become a ferroelectric material at very low temperature. However, that's not what happens in practice. And as you can see from this experimental data, the phonon mode deviates from the Curie-Weiss law, and it saturates at a certain point to a finite value of its energy, which is finite. And the reason why this happens is that at very low temperature, quantum fluctuations of the nuclei become important and stabilize the paraelectric phase. So these materials remain paraelectric down to 0 Kelvin, even if we just fit the higher temperature result, it seems that it should go into a ferroelectric phase transition. However, if we try to do some calculation using ab initio density functional theory, we see that many different exchange correlation functional, from GGA to meta GGA, hybrids, and even RPA calculation, all of these agrees that the paraelectric phase should be unstable, and it actually is a saddle point of the energy landscape. And so why is this material, so are the theories that we use to describe this material completely wrong, or something else is happening? And actually what has been proved in this work by Carla Verdi et al. Is that quantum fluctuation of nuclei, even at very low temperature, are enough, even in the deepest case, which is RPA functional, it's enough to make to give enough energy to the ions to overcome the barrier and then create a quantum ground state that is actually paraelectric. So the material, even at 0 Kelvin, has enough energy, 0 point energy is sufficient to overcome the barrier and create a state in which the system is actually stable in the paraelectric phase. So the point of this material is that at low temperature, we need quantum fluctuation on ions to describe its paraelectricity. However, it has been shown in two different independent experiments in 2019 that if we take this paraelectric phase of strontium titanate and we shine under a very strong terahertz pulse, it induces a coherent motion, which results in the breaking of the inversion symmetry and the generation of a ferroelectric phase, which is metastable in time, and so up to few tens of picoseconds in one of these studies that we will analyze today. So it seems that Terra's radiation is driving the system out of equilibrium, and after these dynamics, the system reach another state, which is ferroelectric. So this is something that cannot happen in equilibrium because the ferroelectric state is unstable at equilibrium, but it's happening apparently experimentally only if the system is irradiated with terahertz laser. And indeed, how did experiment measure this inversion symmetry? Was using a probe which was second harmonic generation, which is generating a signal only if the inversion symmetry is broken in the system. And so while the experimental setup was able to tell us that there is indeed the generation of a phase which is breaking inversion symmetry, they are not telling us anything of what is this phase actually a simple ferroelectric, is more complex. So it was very difficult to understand, impossible from the probe occurred by the experiments. And so there have been other experiments try to address this issue, and in particular, one very powerful technique is to use X-ray as probe, as I was anticipating. In fact, with X-rays, we can actually have a much better understanding and a much better description of the actual nuclear motion that is happening. And so what happened in this other experiment by Cosina et al., published in Nature Physics, is also in 2019. So they shine light Terra's pulse into the sample, and then they observe after a variable amount of time the elastic X-ray scattering on a 2-2, 3 reflection plane. And so in this way, they were able to track the atomic motion really as a function of time. And if you Fourier transform this signal that they got, you can actually see that even if you pump a frequency which is very low and is in resonance with the soft ferrometric mode of this material, they are able to excite higher frequency modes at 5 and 8 terahertz, here displayed by this plot in which they use a variable size window on the time to get a time resolved Fourier transform of the signal. And so you can see that it's generating in time this phonon is pumping a low energy mode, and this low energy mode is upconverting, is transferring energy to higher frequencies at 5 and 8 terahertz, which is very interesting and seems to tell us that this dynamics is very complex. So it's not just the ferroelectric mode that moves and drives the system out of equilibrium and in a ferroelectric phase, but it's actually interacting anharmonically with other modes in the system, and the real picture of what's going on, it's really complex. So we would like to have a tool to simulate these things completely from first principles that doesn't need to rely on a specific parametrization or a specific choice of which mode to include in our modelization of the system to be able to describe how things propagate. And so we would like to be able to simulate everything from first principle, both electrons and nuclei. And since in this case we are pumping on terahertz radiation, and strontium titanate has a band gap which is of the order of 3.2 electron volts, so it's higher than visible light. We actually are not exciting electrons directly with the pump, and so we can separate the nuclear dynamics, which occurs in a femtosecond time scale, and assume that the electrons remain in their ground state, and so within the Born-Oppenheimer approximation, which also. And instead, we need to solve the full time-dependent Schrödinger equation for the nuclei in this thing. And we need to go in the quantum dynamics of nuclei, because as I showed you at the beginning, it's very important. Quantum effects on nuclei are very important to determine the phase, because without quantum effects, the material is ferroelectric at low temperature. And so we cannot use classical molecular dynamics or Ehrenfest dynamics or ab initio Born-Oppenheimer molecular dynamics to study this problem. And but the problem is that solving the time-dependent Schrödinger equation for the nuclei is very complex, and so we need some kind of approximation, some kind of methodology. So the method we developed is the so-called time-dependent self-consistent harmonic approximation, which works very similarly to time-dependent density functional theory or time-dependent R3-Fock, but instead that targeting electrons, we target nuclei. And so the idea is that we parameterize the wave function as a Gaussian wave packet, which is usually quite good for describing nuclei in a lattice. And then we minimize the Dirac action, so by optimizing, so we optimize the parameters of the Gaussian as a function of time by minimizing the Dirac action. And if we do this, we obtain self-consistent time-dependent Schrödinger equation for the nuclei, which, as I told you, recalls a lot the time-dependent density functional theory, with a difference that now this Hamiltonian that propagates the quantum nuclear wave packet is self-consistent, and it is harmonic. That gives the name to self-consistent harmonic approximation. Indeed, we can extend this theory also at finite temperature, and we just need to replace the time-dependent Schrödinger equation with the time-dependent Liouville-von Neumann equation for the evolution of the density matrix. And by deriving these equations, we actually can get equation of motion for all the parameters of the Gaussian wave packet, which are average position of each nuclei, their average momentum, and then since we are describing quantum fluctuation, we have also correlators. For example, position quantum correlator, momentum, position momentum, which are typical of which define our Gaussian wave function or density matrix, and essentially it's describing the quantum nature. And so you can immediately recognize that the first two equations resemble a lot Newton equation, but with a correction that is now the force that is changing the momentum, it's averaged over the quantum wave function. And then we have a pure, as I was anticipating you, contribution which accounts for the quantum dynamics of the motion. And here you can see a very simple example of this theory in practice. We have a double well potential under a variable electric field, so that is essentially making the system go one way and the other. And you can see on the bottom left corner the exact numerical solution solved by the Totter theorem, and which is possible to do in one-dimensional systems. And on the right, instead, the time-dependent self-consistent harmonic approximation, which, as I was anticipating to you, it's a Gaussian. It's constrained always to be a Gaussian. And here we see the average position of this particle, which is quite good with respect to the exact results. So this is how the theory works in practice. The difference with respect to the exact result is that indeed we can employ this theory to simulate a much bigger number of atoms, up to hundreds even, and that's exactly what we did. And for example, if we take now only the one phonon mode, so which is the ferroelectric soft mode of the strontium titanate, and we displace it and we do the quantum dynamics, we can see that indeed it evolves around zero because it's a quantum paraelectric, while if we do the classical limit of the equation, so only the Newton equation, and we evolve them, we have a completely different dynamics, which is centered, off-centered with respect to the zero, which is paraelectric phase, which indeed we obtain a fake ferroelectric phase because classical dynamics doesn't account for the quantum fluctuations. And however, we can also solve the full system. Here we have the dynamics of the titanium atoms. I took one titanium atoms along the same direction of the polarization of the incoming electric field, and here is the average position of the titanium hydrogen as a function of time, and we can see that what happens is that we have when the pumps arrive, we have an excitation and then a slow decay. And indeed, if we do the Fourier transform of this curve here, we get that not only we excite the soft ferroelectric mode, which is the one in resonance with the pump, but we have the appearance of other peaks, exactly like was observed in the experiment. And if we compare with the previous experimental figure that I show you, you can see that it's very similar. But not only, we can do more, because instead of taking titanium atoms, we can actually simulate as a function of time the result of a X-ray elastic scattering experiment. And so we compare here our result with the experiment I was showing you before. And so we can immediately notice a difference, which is the position of the mode we are exciting. In our simulation is a bit higher. This is due to the choice of the exchange correlation functional, which we use now GGA. We are working to go beyond this approximation right now. But despite for that, we see exactly the same feature that appears also in the experiment. We see this upconversion in which we are populating two higher energy modes, which are exactly the same observed into the experiments. But we can also do more, because indeed X-rays are very good because it allows us to see the atomic motion, but they weigh different atoms based on the number of electrons that each atom have, and also based on the reflection plane that we choose. We may or may not see different phonon modes. So we define a way to study how energy can be partitioned between different modes, and in this way we can see how the energy is flowing from the mode we are pumping up to all other modes. And here you can see, here in red is the Fourier transform of our pump pulse. And so you can see as a function of time, this is where our pulse is arriving and what is its spectral components, which is in resonance with this, which is the ferroelectric mode, which is indeed the strongest mode pumped. And you can see how after a certain amount of time, other modes appears. In particular, these two were exactly the same modes that were identified also in the X-ray experiment, but there is also a much higher frequency mode, which was not identified in the experiments, which has quite a lot of energy, which is transferred to this mode. And then after few picoseconds of the dynamics, a lot of other modes starts getting populated, and these other, while all these three modes here are modes which are present in gamma, all these other modes are phonon modes outside gamma. And so actually the dynamics is really complex, because almost all phonon modes gets populated due to an harmonic coupling between them. And indeed, what happens is that this gradual population of all the phonon modes is depleting the energy of the original mode, and in this way we have the damping mechanism that is occurring even if we are not putting any damping in our simulation, because energy is automatically flowing from the phonon that we pumped into all the other modes in the system. But what about the ferroelectricity that I spoke so much at the beginning? So if we analyze our trajectories, we see we don't see any breaking of the inversion symmetry. So it seems to suggest our simulation that we don't see ferroelectric induced phase transition. However, what we observe is a huge non-equilibrium stress that acts on the cell. So if here is where the pump arrives, and you can see all the components of the stress tensor here. And as you can see, there is a huge stress of up to 2 gigapascal when the pump arrives. And then it remains a non-zero value of the stress, even if not quite small, but which is still persistent after the pump arrived. Interestingly enough, this system as a phase transition into a ferroelectric phase if we strain a bit the system. And in particular, if we use PB-Sol, which is the functional we used, we can see that after 2.3 gigapascal, the system become ferroelectric. So we have the ferroelectric phase transition. So we know that PB-Sol is overestimating a bit this value, because it's also overestimating the energy of the soft phonon modes as the previous. So the real value of the pressure is probably much lower, so around 1 gigapascal. And the interesting thing is that to have a spontaneous inversion of the symmetry breaking, we need a persistent strain, a persistent stress that is of the order of 1 gigapascal. And so to explore a bit if this is possible, we change the temperature, we tune a bit the temperature, and we see that going from 0 Kelvin to 100 or 200 Kelvin change completely the stress, and you can see that the stress generated is much higher and very close to the threshold that can sustain the ferroelectric phase. But even more, if we tune the frequency to be off resonant, this is interesting. If we have a frequency which is off resonant with respect to the ferroelectric mode, now we observe a persistent stress after the pulse already it disappeared. After 2 picoseconds, it disappeared completely, the pulse, and you can see that still after 5 picoseconds, we have oscillating stress of the order that reach 1 gigapascal, which would be enough to create a ferroelectric state. And the reason why pumping of frequency to high frequency induce a bigger stress on the cell is due to nonlinearity. In fact, the frequency of the mode change with the pump. The more we pump, the more energy we give to this phonon, the more its own energy respond and change and increase. And so we need a balance between pumping to higher frequency, which will be the resonance with a higher value of the field, and not going too much out of resonance, because otherwise we don't excite it anymore. So, and by pumping slightly off resonance, we get a much higher response. So I want to acknowledge Francesco Libbi, which did mostly of the work. He's now working at Harvard University with the group of Boris Koziski, and he was the one who implemented the equation that I showed you before, and derived also a generalized Verlet integration scheme to integrate them efficiently and prove them to be an asymplectic algorithm to conserve the energy and so on. And he also developed the code to compute the time-resolved X-ray diffraction and run the simulation. So he actually was the guy who did the work. So I want to really acknowledge him here. And so let's go to the conclusions. So we have now a methodology that can be used routinely to compute out of equilibrium dynamics of nuclei accounting for quantum effects. And in particular, it's very interesting because even without, now that we allow the system to interact with itself with all the degrees of freedom, we have enough degrees of freedom to observe smearing, for example, automatic decay of energy of the phonons, because the energy is simply flowing between different modes of the systems, and we have access to the full cascade of energy since we pump up to all the cascade that lead in long time to thermalization. And so we have a new tool to access all this out of equilibrium information, even in systems that exhibit a strong quantum fluctuation like in strontium titanate. And even if we didn't observe directly the breaking of the inversion symmetry, we observed a huge non-equilibrium stress, which is a mechanism that can actually explain the symmetry breaking in presence of a pump, or the stabilization of a metastable phase with a strain which is present in the system. So thank you very much for your attention, and I open to answer your questions.
Thank you very much, Lorenzo, for the interesting talk. So if you want to ask a question, please go to the reactions section and raise your hand. Yeah, Tom van Waas has a question.
Hi, can you hear me?
Yes.
Okay, thanks for the interesting talk. So can you elaborate a bit on the need of driving the system at like particular frequencies? Because you said, okay, we use a GGA, so it doesn't really like matter so much for the excitation frequencies, which like resonant frequencies we observe, but on the other hand, it matters for driving the system. So can you maybe clarify a bit more where it is actually relevant to be on like the right resonance frequency for driving?
So yes, so essentially what we did here was indeed rescaling. Since we are pumping on this mode, on the soft ferroelectric mode, we also rescale the frequency of the pump to be in resonance with the system. If this is important, because if we are not in resonance, essentially we are not exciting the system, and so we want to have the same as possible condition with the experiment. We have other results, which I've not shown, in which we actually obtain the same frequency as the experiment by straining. So if you take a GGA instance and titanate, you do a simple strain, you can almost match exactly, find a strain that in which you can almost match exactly the experimental spectrum, and indeed the results don't change very much. So we still observe the same phonon upconversion, change quantitatively. Indeed, the different energy that is transferred, the exact energy is different, but not so much. Right now, we did simulation pumping only the soft phonon mode. We want to also, indeed, we want to explore also the possibility to pumping other modes. For example, the work of Caralleri that I show, they didn't pump the soft phonon mode, they pump a higher frequency, a transverse optical mode at higher frequency, and they observe down conversion in energy. So we plan also to do this kind of simulations, which are very interesting. So essentially, we must pump a infrared active mode. That I think is the important thing, because otherwise we cannot drive the system out of equilibrium. But then we can do. Yeah.
Okay, thank you. Then there's Nicolas with a question.
Can you hear me?
Yes.
Yeah.
Yep.
I was curious for your equation you showed. So you have the equation of motion of the ions. Can you include also the lattice dynamics as an extension, like basically this kind of parallelogram dynamics, if you wish, but here.
Exactly. So that's something we want to do. Actually, indeed, because since we have the strain, we saw this strong stress. We want to see. We need to include that term if we want to actually have a full. So if we want to have a description with a variable cell. So what we are doing right now is to just having different simulation varying the strain, a different value of the strain to see which cell reproduce the one that will have a long time at zero stress value. But yes, in principle, it is possible to do. It's not easy. It's not that easy. Also, it's not that easy to find then integration algorithm that keeps the conservation of energy and everything. But yes, so we want to go in that direction.
Okay, perfect. Thanks.
Thank you. Then Andrea has a question.
Hey, hi. Can you hear me?
Yes. Hi.
Yeah.
Hi. Curious about those equations. I mean, they look really interesting. When you go out of equilibrium in general, the biggest problem in the quantum description is that you have time in no locality. This is the biggest problem, right? So all the kind of approximation like GKBA, these kind of things are to deal with this no locality. Instead, your quantum dynamics is fully local in time. Is this an exact property of your theory, or this consequence of an approximation?
So this is an exact property of the theory, which is indeed an approximation, and the fact is that it is possible. What we proved in this work here is that this theory actually it is in some way a semi-classical theory. So in the sense, you see, we recover some the Newtonian dynamics. So what happens is that you go to finite temperature, so there is no H bar in this equation. That is the point. So the classical limit of this equation are themselves, and this means that the fact that we are evolving a quantum state depends only on the initial condition. So we must prepare the initial condition in a quantum state, and then we are evolving a quantum dynamics. If we prepare, for example, the initial condition in a classical state, but at finite temperature, we will still have correlators. So we still have this equation, and we will evolve a classical system. So somehow the theory, which comes out from also this equation here, is in some sense semi-classical. And the reason why it is so is that this Hamiltonian here is harmonic. And since the Hamiltonian is harmonic, quantum and classical dynamics in harmonic Hamiltonian behaves in the same way. So I don't know if I answered a bit your...
Yes, thanks.
Okay. Then a question by J. Mo. I don't know if my pronunciation is correct. But...
Hi, hello. Hello.
Hi.
Can you hear? Can you hear me?
Yes.
Yeah, okay, so my question is whether you can, you mentioned that you can calculate the dynamics of not just the equilibrium position, but also this correlation. So do you see any local correlation of this ferroelectric displacements in your dynamics?
That's we are actually, so we actually haven't looked at it yet. But this is something we want. So right now, what we did, actually, we only looked to the equilibrium position. Also, when computing the X-ray, I have to say we computed the X-ray assuming ions were in their equilibrium position when we computed the scattering. Indeed, it should be possible. Not only should be, the correct thing to do should be to use the full expression of the wave packet, which accounts for the correlator, and that should be the exact thing to do. Yes, so we probably will do that in the future. We have not looked at it. So thanks for the comment.
Thank you. Thank you.
Okay, thanks. I had a question on this this simulation that you showed for the double well, where you compared the exact result to the results obtained with your approximation.
Yes, yeah.
Yeah, so there, of course, in that double well, the barrier is not very high.
Yes.
So I guess if you increase the barrier, it's going to look less and less like a Gaussian. So is what we have there, is that something that corresponds to what you have in your strontium titanate, or?
So I wouldn't say, because in strontium titanate, actually, the quantum fluctuation, so it's very similar to a Gaussian, the wave function, because your quantum fluctuation are enough to jump across the barrier, so the barrier is not that high. So the one that I show you in the previous slide, this one here, is a really big magnification. This is a very big magnification. So you can see it's only 7 millielectron volt per formula unit, so it's not actually that much of a double well. So actually what you see is that the 0 point energy is much above this barrier, and therefore your wave function will be differ from the Gaussian, so we'll have a deformation with respect to the Gaussian due to that fact, but it will still be a single picked function, and so the Gaussian remains a good approximation for it. So for example, yes, so as also in this work here, what they do is they actually use a Gaussian approximation, but they study the equilibrium property to see the ferroelectric transition. It works very well. Okay.
And about the calculations, you said that you could treat up to an order of 100 atoms, nuclei. Yeah. So does this mean that you're doing a supercell calculation?
Yes, exactly. So we are using supercell, yes.
And also, so the DFT calculation that you use, is that for a given for a single nuclear distribution, or
so what how it works is in this way. So what we did so we ran everything on a laptop, and what we did, we trained on DFT simulation and force field. But in principle, the number of calculations we do, it's completely feasible to do also everything ab initio, because it's not that much. And so what actually happens here is that the only real part in which we need ab initio results is to compute this average here and this average here. Now, this second average here seems very complex because it's like an average of phonon calculation, which would be very expensive to do. However, since this bracket here is on a Gaussian wave function, we can integrate by parts, and then that's actually becomes the first derivative of the potential times a displacement, which is the derivative of the Gaussian wave the Gaussian distribution. And so in this way, we actually only have to rely on forces to integrate the equation of motion. So we actually, for a wave packet, we generate a set of random, like 500 random structure distributed according to the Gaussian distribution of ions. We compute energy and forces, essentially forces for each of these calculation, and then we can do one step of the dynamics, and so on and so forth. So this is what we are doing right now, we can also do some reweighting techniques to reuse force calculation of previous steps and not having to use them every step. But since we are using a force field, we have not implemented this. So we are using this machine learned force field on top of the density functional theory. We have not used that in this case.
Okay, thanks. Are there any other questions? Okay, maybe just one last one from me. Just in the beginning, the slide that you showed about this paraelectric phase. Yeah, here, no, the previous one, excuse me. Could you repeat the argument here that, so you have these calculations, and I didn't understand here what was the message. So this double
essentially, the message is that all density functional theory, no matter if you do GGA, meta GGA, hybrids, or RPA calculations, all of them gives the paraelectric state to be a saddle point, so to be unstable, if you want. And so that's actually and the reason why the reason why instead experimentally the system is still a paraelectric is because it's stabilized by the quantum zero-point motion. So it's quantum effect of nuclei that are responsible to stabilize the paraelectric phase of Strontium titanate.
So there would be a minimum at 0, or
what?
How would the curves change if you would include this effect?
So essentially what you need to do is to define a positional energy, because then if you have quantum effects, your atoms cannot be on one single position because you will have a quantum distribution, and so you must define a positional energy, which you can do using, for example, Lagrange multiplier on the average position of the energy. And then you can define an energy curvature, and that would be a minimum. You will have a minimum.
Okay, thank you very much. I don't know if there's any last question. I don't see anything. I don't see any questions. So maybe this is a good point to stop. So thanks again, Lorenzo.
Thank you very much.